Hello students, and welcome to lesson 1.5. I can't believe we're here already. In this lesson we're going to be talking about unit conversions and scales, which is definitely something interesting and applicable to all of us. We're going to start by thinking about the idea of a ratio and what exactly is a ratio. So all it is, it's actually really simple. A ratio compares values. How much of one thing is there compared to another? So I think in our lives we constantly are comparing. Maybe we're thinking about, what is the difference between the number of boys in the class versus the number of girls in the class? What is the difference of small dogs versus large dogs at the dog park? There's all kinds of different things that we compare, and we can show these, or I should say represent these comparisons through a ratio. As you see, I have an image here, and I want to just show you different representations of ratios, and one of them can be through a visual representation. So I have these 4 boxes, and I've shaded 3 blue and 1 yellow to show you that I have 3 blue squares to 1 yellow square. But maybe I want to use more mathematical notation, and I'm going to use a colon, 3 to 1. If I actually want to write that in the way that I say it in English, I would say 3 and then the word 2, 1. Or I can even write it as a fraction, 3 over 1. So all of these are appropriate ways to represent having a ratio. Now, why would we ever use a ratio? Well, when we want to represent scaled down images and figures. And a great example of this is in maps. Now, granted, I'm almost positive that about half of you have probably never used a paper map now that we live in the worlds of GPSs. But on a paper map, you have a scale, and the idea is you would want to know if you're living in Smithfield and you decide you want to take a trip to Raleigh, you want to know how many miles that's going to be. And before the world of Google and just typing it on our phones, you needed a way to figure out how many miles is that. And so a scale would allow you to use a ruler to measure the distance between 2 cities, and then you could do the comparison ratio and identify how many miles are between the city. There are many uses of ratios and proportions. Other things beyond map reading are making scale drawings and models, or solving problems, and even cooking. A lot of fields, if you're pursuing something like engineering or something where you're going to build something, you make, if you were going to build a bridge, you would make a scaled model of the bridge. You're certainly not going to make a rough draft image of the bridge and actually make it the size of the real bridge that you're building outside, right? That wouldn't make any sense. Another thing, when I think of scale drawings, I have no idea why I think about this, but I think of a cereal box, right? That's one of those most common things. In the morning, you're sitting down eating your cereal, just looking at the box, reading over the box, and then you say at the bottom of the box, it may say, not drawn to scale or drawn to scale, right? So and definitely ratios can be used, in our common everyday lives. So with that being said, we're going into the discussion of measurement conversions, because we can measure things in a lot of different ways, but sometimes we want it in a particular unit. Just to give you an example, maybe you're following a recipe and it's calling for a certain unit of sugar. Maybe it wants, cups, right? And you don't have a cup. You don't have measurement of cups, but maybe you have different smaller measurements, and you want to figure out, okay, what are the number of, tablespoons that are in a cup, and you want to try to convert that, right? That is the reason why measurement conversions become useful to us, and this process of dimensional analysis helps us to figure that out. So if measurements in 2 different units represent the same actual length, then a fraction formed from dividing those units is a way of representing the value 1. So this actually sounds a lot more complicated than what it really is. It's the idea that if I know that there are 12 inches in 1 foot, I know that there's 1 foot in 1 foot, right? I know that there are 12 inches in 12 inches, right? Sounds a little weird, but that's refreshing your memory, or refreshing the idea that when you have the same thing on the top and the same thing on the bottom, that's equal to 1, right? And what this is saying here is, if I know that there's 1 foot and 1 foot and 12 inches and 12 inches, and I know that 12 inches is equal to 1 foot, then all of these fractions, this one, and this one, are all equivalent to one another and actually equal the value 1. Okay, so not anything too crazy there, but just wanted to make sure that was kind of clear. So conversion factors. Multiplying any measurement by a conversion factor won't change the size of measurement, but it will change the units of measurement. So what I want to make sure you understand is that when you convert something, you're not changing anything about it except the way you're talking about it, okay? So I'm going to use a different word, translate, right? If I'm saying something in English and I want to translate it to another language, for the most part, I am trying to say the same exact thing, but in a different language, right? So it's no different when I convert in mathematics. I may be talking about math in one form, so maybe I'm talking about it in inches, and now I want to translate it, or I want to do a conversion factor and talk about it in centimeters. Has anything changed? Has the actual thing that I'm originally talking about changed? No, it's just the way that I'm talking about it has changed. So the goal of converting units is to multiply by a conversion factor that makes the units that we don't want divide out, which ends up leaving the units that we do want. Okay, so this is really wordy. I apologize. I know you're probably looking at your computer screen right now like, what in the world is she talking about? But it will make a lot more sense when we do some examples, okay? So here we have 1 meter is equal to 100 centimeters, okay? So just thinking about the conversion factors, we're not doing any problems at this point. I just want to make sure that you understand this is saying in 1 meter, there is 100 centimeters. Okay, so that's what the original problem, right? So this is one way that we can write it. Another way that we can write it is in 100 centimeters, there is 1 meter. Okay, neither one of these are saying anything different. Okay, it's one thing I want to make sure you understand. Okay, they're saying the same exact thing. The only difference is which unit am I putting in the numerator versus which am I putting in the denominator. Same thing with problem number 2. I can say that I have 1 inch in 2.54, and I apologize, I don't have my units there. That should be centimeters here. Or I can say that there are 2.54 centimeters in 1 inch. Okay, so the idea is you are welcome to write whichever unit on top and bottom. It does not matter. You're going to choose this based off of what units you're trying to get to. Okay? All right, so convert 25 gallons to liters. So you're thinking about what are you starting with, what are you trying to get to. So you're starting with gallons, 25 gallons, and you're trying to get to liters. And I generally like to highlight this. So in yellow, I'm going to highlight what I'm starting with. I'm starting with gallons. And in orange, I'm going to use a highlighter in orange to show what I'm trying to get to. So I am starting with 25 gallons. And you can write that over 1. And honestly, you can write just 25 gallons if you'd like. I'm showing you that it's over 1 because I want to make sure you understand that all whole numbers are always over 1. So whether I write it or not, it doesn't matter, but you just want to make sure you understand in your mind that any whole number has a 1 underneath it, okay? And the idea is I'm trying to get to the units of liters. So that's what I want to end up with. So I'm trying to get some number here of liters. So when I think about, here's my original, right? Here's what I start with. So I'll write the start. I need to multiply by what we call our conversion factor. So this is what I have to figure out. And I want to make sure that the unit I'm trying to get to is in the top. So you see that I have right here, so I'll highlight that in orange. And then the unit that I start with that I don't want anymore is in the bottom. And the reason why I want that in the bottom is you see I have a slash here because it slashes on the bottom and it slashes on the top. They cancel each other out so that I can then multiply across 25 times 3.785 and I get 95, and the only units left are liters. Okay? I encourage you to take a look at the class section in your textbook on page 60. I think that is a good reference point to think about these conversion factors a little more and to go through all of these different problems. But you also have what is called the dimensional analysis lab this week. And I actually have a second video after this lesson that takes you through some of those problems and just tries to help and give you a better idea of how to complete the process of dimensional analysis. Because I know this isn't something that's very easy. It can be a little challenging to understand at first glance. So as always, if you need any help, or you have any questions, please do not hesitate to ask. I'm more than happy to help. And I hope you have a wonderful rest of your day.